Aloha and welcome. In this video, we're going to be talking about application attacks again, but this time we're going to be looking at it from a programmer's perspective. So we're talking about here memory vulnerabilities. We're talking about buffer and integer overflows, memory leakage, and pointer dereferencing. So we're going to start off with buffer overflows, and buffer overflows have been used for attacks in the past, some pretty famous attacks. So a buffer overflow, well, first of all, let's define buffer. A buffer is a memory region that's used for temporarily storing data while data is being transferred from one place to another. So in these places where you have a buffer, if you overwrite it, if you write too much stuff to that buffer, then you're going to have what we call a buffer overflow or buffer overrun. And that's the programming condition when the size is just too large to be put in there. So if that occurs, what's going to happen is the data, it's going to fill up that buffer and then it's going to write it into adjacent areas. And you don't want that because you don't know what's in there. Is that executable stuff that it's overwriting? You'll get errors. It's possible that they could end up, putting in their own code, injecting that in. So you don't want that either. So you have to be very careful. You have to make sure that you don't have improper input handling. You need to make sure that the amount of stuff you're trying to put in there fits. And you need to have those input validation checks. Another type of overflow type issue we have is integer overflow. So in programming languages, you have the concept of a data type or a type. Data type simply says what you can, what is that data? So you've got floating point numbers, you've got integer numbers, you've got characters, you've got Booleans. Boolean is simply a true false if you're not familiar with that. So if you've got an integer, if it's a 16-bit if it's a 16-bit signed integer, you're going to have values from negative 32,768 to 32,767. And if you go beyond that, you're going to have what we call an integer overflow. An integer overflow isn't good because what's going to happen is it's going to come up with a number, but it's going to be wrong. It's going to go outside of that range, and it may flip over even. So if that happens, you're going to get a number that isn't accurate, and it's still going to trust that number and use it. So you have to be careful about these things because people can intentionally mess up your data if they know where your integers are and if they know you're not checking for values and things like that. Some programming languages like Python, they'll actually automatically adjust their runtime to accommodate a larger value than may result from regular integer operations. So some programming languages can work around that, some can't. So you have to be careful of integer overflows. Another thing we have is memory leaks. So in computers, in programming, you have two essential types of memory. And good memory management is key to making sure that you're using it properly. So stack is this area where we call it temporary memory. But as you're running a program, you have a stack, and your stack is going to have your local variables and your static memory allocations, and you're going to store your memory in there. That's all handled by the operating system, and you don't have to worry about that. There's another area called the heap, and the heap is where you keep all your global variables that are used outside of like inside functions and things like that. Or, well, it can be used in functions as well, but it's used in a different context. So your heap is storing these global variables. It's also used for dynamic memory allocation. The problem with this is your programmer is responsible for handling the memory in the heap. And if you're not, when you're done using some memory, if you don't deallocate it, what happens is you've got this memory, the computer thinks you're still using this memory space or this variable, and you're not, and you can fill it up. And if you, or worse, you can, the computer thinks it's being used and there's no way to reference things there, then you've got a problem because if you don't deallocate your memory, you can get a memory leak. And that's the occurrence when the program allocates heap memory, but doesn't deallocate it when you're finished with it. So it's the improper memory management by a programmer. So you don't want to have that happen, because what's going to happen is as you run, you use up more and more of your memory, you're going to get to the point where you use it all up, and then it's going to crash. So that's the danger of not managing your memory properly. And some it's not mentioned in the book here, but Some programming languages have dynamic memory allocation and deallocation. So we call it trash collection. So you may have some languages that are taking care of this, but some don't. So you have to be careful of that. And then we have something called pointer dereferencing. And pointer dereferencing is a very difficult concept even within programming. So you'll really need to bear with me on this one. But a pointer is a program variable that stores a memory address. So normally if you say like variable A and you put a number, a value in it, it says, okay, variable A, it's going to point to here and we're going to put the value in there. But when you're talking about pointers, you're actually talking about, you're pointing to a memory place, a place in memory where that value is stored. So we have these concepts of pointers. We have pointer dereferencing or object dereferencing, and that's dereferencing is essentially when you're looking at the value, when you're actually looking at the thing that it's pointing to. So that's a tricky concept for most people. So I'm going to go ahead and share my screen with you here so that you can understand that. There's a demonstration of it in the book here. So I'm going to go ahead and open up and look here. So we have here a simple program. We're going to start out. This is a C program. C is still used. It's an old language by, I think, Kernighan and Ritchie. I think they're all passed away at this point. At least one of the two is. But anyway, we start off with an integer I, then we've got a pointer to I. So that star, the asterisk, P, that is a reference to P. It's a pointer. So when we start out, we say, okay, I is going to be here at memory space 0x01, and P is going to be over here at 0x03. So here's the memory that they take, the memory space that they're occupying, and here's the values that are in there. So right now we don't have anything because we're just allocating these. So now we're going to go to the next step, and that's I equals 7. So at this point, we're going to store the number 7 in I, and 7 in hex is going to be 0x07. So it's stored as 0x07. Then the next step, we're going to say the address of memory location storing integer value 7 is stored in integer pointer P. So let's look at that really closely. So what we just did was we didn't assign a value here. We didn't assign I. If we just said I, it would assign 7 there. So it would be putting 7. We're saying P is going to be equal to the thing, that's over here. So we're saying whatever this points to, that's what we have. So we've got a pointer to this location. So if they change this, this is essentially pointing to whatever they changed it to. So bear with me here. So the next step is stars. It's explaining that star is the dereference operator in the C language. So star P dereferences P, and star P equals 9 stores integer 9 to the memory location pointed to by P. So what it's doing here is it's saying, okay, P is pointing to 0x01. I am going to store 9 in the place that I'm pointing to. So this is equivalent to saying I equals 9 because we're pointing to the same memory location. And that's the thing that a lot of people have trouble understanding. We're not assigning the value to P. We're assigning it to the value of what P points to. So let that sink in a couple of times, and then go down here and answer some of these questions. And it will really, it'll really challenge you. So keep that in memory, and then in mind. So memory injection is something that's important. So the reason why all this is important is memory injection. That's the security vulnerability that involves the manipulation of the application's memory to execute malicious code or gain unauthorized access, extract sensitive data, or disrupt behavior. And the example they give is injecting code into a web application's memory could allow access to sensitive user data or control over the application's functionality. So that's why you have to be careful with all of these things, because you could inject malicious code into it. You could disrupt the proper functioning of it, or you could get access to things in memory that you shouldn't have access to. And hackers are very good at figuring this out. So there have been a number of cases in history in hacking, famous hacks, where they exploited buffer overruns or pointer dereferencing issues. So that's it for this section. If you have any questions, feel free to reach out. I'd be happy to help you. If you don't have any questions, then I will see you in the next video. Aloha.